How to draw Newman projections. Okay. So the way that we're going to draw Newman projection, given a molecule, say we have some molecule like this. Hydrogen here, and a bromine here. You draw a Newman projection as if you're looking down the carbon-carbon bond. So this would be a carbon right here, and this would be a carbon right here. So we're going to be looking down this bond. If we're going to look down that bond, we're going to firstly look at this carbon. The molecule that's in the plane is going to be the molecule we're going to put at the top. Notice this segment here, this carbon attached to 3 substituents, this is the front, whereas the back is the ring with the 3 substituents coming off. If we're looking at it from this side, the bromine is going to be in the front. Therefore, bromine is going to be on one of these 3 sticks. So, looking here, we have a methyl group, a bromine, and there is a secret hydrogen which we could draw in. So, the one molecule in the plane is the one we're going to draw up. That is going to be our methyl group. We choose a side for the wedges to go on, and we choose a side for the dash to go on. In this case, we're going to choose the wedges to go on this side, and the dashes to go on this side. You can do vice versa. Regardless, you'll get the same Newman projection. So, CH3, the wedge is the bromine, meaning the bromine will go down here. And the dash will be the hydrogen, which goes down here. Now, in the back, we see that we have a methyl group here, and a methyl group here. And so, the methyl group is in the plane. We'll draw one here. On the dash, we have a methyl group as well. So there will be a methyl group here, and there will be a hydrogen on the side of the wedges. Now, ideally, we would like to have our Newman projection in the antiperiplanar conformation. This means that the leaving group will be axial, so it'll be on either one of these positions, and on the other side of that axial will be the proton. We have to rotate this as a result to obtain that projection. So let's start with the front. We want to get a molecule with bromine on the top, because bromine's in the front of the, looking down this bond, bromine's on this carbon, so it's going to be in the front, and we want it to be in one of these 2 positions. it can't be in this position because it's in the front, so it has to go up. If we rotate the bromine to the methyl will go to where the hydrogen is, and the hydrogen will go to where the bromine was. Now, let's do the same for the back. We want the hydrogen to be antiperiplanar to the bromine, which is our leaving group. This is a rotation. So we're also going to have to rotate the back. The hydrogen would go to where the methyl is. Methyl goes to where this methyl was, and this methyl goes to where that hydrogen was. Now, this is our antiperiplanar conformation. And it is ready to undergo an E2 reaction. What that means is, because it's in the antiperiplanar conformation, when the leaving group leaves, we'll have the bromine come out. And the bromine is going to attack the hydrogen, allowing these electrons to form a double bond. These molecules, these substituents, will squish. So we'll get something like this. H and CH3 and this. These, since these squish, they come close together. And this is our double bond in a Newman projection. So if we were to draw this back into 2D space, we would get something like this. We'd have CH3, 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 and an H. So again, we look down this bond, the CC bond. We choose the plane. Methyl's in this plane, and methyl's in that plane. Wedges go on this side, dashes go on this side. We rotate the molecule to get the antiperiplanar conformation, where our leaving group is on the top. It could be on the bottom in some case. If we look at it through this lens, then it would be on the bottom. And our proton is directly across from it, also axial. And when our leaving group leaves and attacks that proton, the substituents on the side squish together to form this molecule. And that is the Newman projection.